Counters are sequential circuits where flip-flop outputs collectively represent a number. Typical counters will increment up or down by 1 every time a clock ticks. However, as we'll see, it's possible to design counters that go beyond this as well. A counter is a type of circuit that resides in the category known as finite state machines, which is a topic we'll explore in more detail in the next chapter. While that term may sound scary, it simply means that the outputs of the flip-flops have only a finite number of values that they can take on. For a counter, those values would represent the number that the counter has at any given time. The number of flip-flops required in a counter circuit is equal to the number of bits required to represent the largest number in the count sequence. For example, if we want a decade counter that counts from 0 to 9, the number 9 requires 4 bits to represent, so the counter would need 4 flip-flops. A counter that includes the highest number of 58 in its count sequence would require 6 flip-flops. The sequence that a counter circuit counts out can be represented by a state diagram. Each state is represented by a circle. Shown on the screen is a state diagram for a decade counter that counts up. For a counter, the number in each circle represents the decimal value of the binary number represented by the output of each flip-flop. In this example, state 5 represents the interval of time when the outputs of the flip-flops are 0, 1, 0, 1. The arrows represent the transitions taken each time the clock ticks. A state diagram can be used to represent a circuit that can be designed differently depending on the requirements or desires of the circuit designer. We'll learn the specifics of how this happens for each type of counter in their respective video. All counters, regardless of the type, are deterministic. This means that no matter how complicated the counter, a state diagram can be derived for that counter. Students are frequently interested in generating random numbers, and perhaps stumble upon articles describing counter circuits that are complicated and may appear random. However, any digital counter is deterministic. If provided with a circuit diagram, a state diagram can be derived. The counter circuit will, without fail, count through the exact sequence represented in the state diagram every time it runs. While we cannot truly generate random numbers in this manner using digital hardware, in student design projects it's common to build a regular counter and clock it with a speed that would prohibit a human from gaming the system to select any specific number. Upon pressing a button, for example, the current value stored in each flip-flop can then be stored in a register. Two major types of counters are synchronous counters and ripple counters. There are other types of counters covered in the class textbook, but we will not be covering those specifically in lecture. We'll cover synchronous and ripple counters in the next 2 videos. We'll see how to represent counters by a state diagram, use a transition table to design a synchronous counter, and use features of flip-flops to design ripple counters.